Hello, everybody. We are starting up a brand new chapter, brand new world of organic chemistry. So this is chapter 21, and let's jump into it. So, quite a bit of stuff to talk about in this chapter, and we're going to be focusing on just section 21.1 today, talking about hydrocarbons. So, a lot of stuff to talk about in the world of hydrocarbons. We'll go on to talk about unsaturated. So, these are going to be ones with double bonds and triple bonds. Talking about isomerism, how different structures can have the same chemical formula. We'll have a lot more groups besides just carbon and hydrogen, such as alcohols, which we've seen before, amines, which we've also seen before, like ammonia, and then a whole bunch of other types of functional groups, and then finally polymers. So today, though, let's focus on section 21.1, Intro to Hydrocarbons. We are going to learn how to identify and name different types of hydrocarbons and write out their formulas and structures and talk about some of their properties, things like that. First of all, though, organic chemistry. What do we mean by organic, right? Farm fresh, locally grown, perhaps. But in the world of science, organic means compounds that contain carbon. Um, they use this term organic. You can think of anything in life that we deal with revolves around compounds that are structured from carbon chains. So you can see that this is a very broad topic. Organic chemistry is very, very broad. And so we start piece by piece. We're going to talk about carbons and hydrogens. So that's where we're going to be. And again, we're talking, they come from fuel sources. They're in our plastics. They build up DNA, all of our proteins in our body. Wow, I cannot write today. We'll just pretend I wrote that out correctly. Proteins, all this type of stuff is the world of organic chemistry. Pharmaceuticals, drugs, aspirin, any type of pharmaceutical drug is the realm of organic chemistry. So it is because of the fact that carbon can form these chains with each other that we can get a huge amount of different, basically an infinite amount of different types of compounds. So today we're talking about hydrocarbons. Carbon and hydrogen, that's it. So when we talked about Lewis structures a long time ago, and we talked about methane, for example, and we learned how to draw the Lewis structures, and we said that carbon has 4 valence electrons, so it needs to make 4 bonds with something to get an octet, and hydrogen just needs 1 bond. So carbon will always have 4 bonds surrounding it if it can. So if you see a carbon, and we're talking about hydrocarbons, and let's say you see this carbon right here connected to this carbon, what is left out? Well, we need to fill this entire thing with something else. And it needs to be bonded to something that's going to be bonded to these hydrogens. So these are simple hydrocarbons, carbon and hydrogen bound together. And specifically, these type of compounds, they can be used as fuel sources. We see a lot of combustion reactions using hydrocarbons plus oxygen to give us the combustion reaction. And they're the foundation of all the other classes of organic compounds. So this is how we write them on paper. This is probably a better idea of what they really look like in terms of the physical nature. This is called a space filling model. And you'll notice there's not as much space in here as we might think when we draw them on paper. So this is more of a 3-dimensional model, and it shows it's going up and down. The carbon centers are here. And we can't quite see the tetrahedral nature, but this is a better idea of showing how much space these electron clouds take up and these atoms take up. So remember, this is a carbon atom. This is a hydrogen atom. They have physical space. They take up physical space. So this is an 8-carbon unbranched hydrocarbon. So let's think about the geometry again. When we talked about molecular geometry back in the day, we learned that something with 4 things connected to it, don't mind my emails that are popping up in the background. Okay. 4 electron domains, and there's 4 molecular domains too. So there's 4 things bonded to it, and 0 lone pairs. Oh boy, I'm just a mess with my writing today. We said that takes on a tetrahedral geometry. So carbon center, we'll always see this. If it has 4 things bonded to it, it's going to be sp3 hybridized and no double bonds. So that's that tetrahedral geometry with sp3 hybridization. So if you have a whole bunch of these, what really happens is they form more of this kind of structure, a zigzag, where they're trying to keep their tetrahedron shape. And this is not 3-dimensional, you'll see, but this is kind of the best I can do on paper for now. It's really this kind of zigzag shape. And they try to form tetrahedron centers at every single one of these carbons. So this is sp3 hybridized, sp3, sp3, sp3. These all have tetrahedron geometry. And here's a better view of that with just looking at methane here, CH4, or we can just draw it flat like our Lewis structure, or you actually try to draw it 3-dimensionally. So here's our tetrahedral geometry here. On paper, if I wanted to try to mimic this, maybe I would go like this. I would keep 2 in the plane of the board, or plane of my iPad here, and then I would draw 1 with wedges, or dashes rather. Let me draw those better. I'll draw my wedge first. A solid one means this one's coming out of the board, and this one's going behind the board. That's how I would try to draw a 3-dimensional tetrahedral structure for carbon. So this is how we try to depict things flat on paper. So this was our space filling model back here. And we're talking about other types. So that's the most realistic representation, considering the relative sizes of the atoms and how apart they should be. So you can see the overall shape of the molecule, but a lot of it's hidden. Ball and stick is a little bit less detail, and it shows the bond angles better. So let's actually look at these. So here's space filling. Here's the ball and stick model. You can actually see those bond angles now. So this is 109.5 for tetrahedral geometry. So, and it shows that if it's going to bond here, it's going to try to get these out of the way. So these are going to go down, then it's going to go back up, and these are going to go this direction. So it's 3-dimensional, but also helps you represent the bond angles better. This is the structural formula with bond angles. So I was trying to draw CH4 like that before, remember? Just CH4. So I was doing this. Oh, I'm running out of space. Let's pretend I have more space for a second. I'm going to zoom in. CH4. So remember I was drawing 1 out of the plane here, and then 1 drawing back that direction behind us. So that's what this model's doing here, but it's going to use all of these straight lines here that aren't dashes or wedges would be flat on the surface. And then the rest of these are trying to show you 3-dimensional directions. So the dashed lines are going away from the page, the solid line are coming forward out of the page. And it's arbitrary how you draw these. You could have drawn this H with dashes or this one with dashes. You could draw them however you like, but they have to be going some direction to show the 3-dimensionality of our hydrocarbons. Now we can continue to draw them. Like I said before, this is more of the typical Lewis structure style and we do this a lot in organic chemistry. A lot of times we're omitting lone pairs. Obviously for carbon and hydrogens, we don't have any lone pairs. But if we had something like ammonia, right? Remember when we draw NH3? For a Lewis structure, you want to make sure you have the lone pairs there. In organic chemistry, a lot of times those are omitted. Oops. My eraser is too big. So you'll see structures like that. It doesn't mean the lone pair isn't there. It just a lot of times you won't see these drawn in organic chemistry. So don't be surprised by that. But it's always safe to just add the lone pairs. It's always a better idea to add them, in my opinion. Here is what we would call the condensed structural formula. So notice this C is connected to 3 H's. So it's CH3 right here. That C is connected to carbon, and this is connected to 2 H's. So that's a CH2 then another CH2, and finally it ends with a CH3. And we can write this out, just CH3, CH2, CH2, CH3. Notice this is not saying that this H is connected to that carbon group. You have to remember that the carbon groups are going to connect to carbon groups. You're not going to have an HCHC kind of chain in the middle. Hydrogen only wants to be bound to one thing. So these condensed structural formulas tells us the order of which these are actually connected. Or you might see it like this. So since there's a whole bunch of, there's multiple CH groups in the middle here, you could put this in brackets, say there's 2 of these CH2 groups instead of writing them all out. Because you can imagine this chain getting really long. So that's one way you can do that. Now the actual molecular formula, that's just counting up all the elements. And it's like writing out methane again, CH4. But if you have C4H10, there's 1, 2, 3, 4 carbons and 10 hydrogens. Notice this molecular formula does not tell us anything about structure. It doesn't tell us how the carbons are connected together. This does at least tell us that these are connected in a straight chain. We're going to learn in the next parts of this chapter that this does not represent structure because we can have multiple C4H10 molecules with the same formula, but they could be connected differently. All right. And there's my phone going off now. You try to do your best. With all of these silenced devices, it's a mess. Okay, so these are the definitions of what I just talked about. Structural formula similar to a Lewis structure, condensed formula, molecular formula. So let's talk about, so that's how we represent these things. All right, so in the world of hydrocarbons, we have things called alkanes. And my pencil battery, I'm getting just wrecked by messages today. Alkanes versus alkenes or alkynes. And we also have aromatic hydrocarbons. We have all kinds of different types. We're going to talk about alkanes right now. So what an alkane is, it's a hydrocarbon that has only single covalent bonds within their molecules, as in there's no double bonds or there's no triple bonds. And we call these saturated hydrocarbons because it's like the hydrocarbon chain is saturated completely with single bonds to hydrogens. There are a maximum amount of hydrogens bound to that hydrocarbon chain. So they can't bond to any more hydrogens. So we call these saturated hydrocarbons. And sometimes we call unbranched hydrocarbons like this. This is unbranched because we don't have any carbons chains branching off to this direction or this direction. So we would call this a straight chain, even though we know it's not a straight chain, right? It's a zigzag, but we still might refer to them as, quote, straight chain hydrocarbons if there's no branching coming off of them. So just notice that. So here are the first 10 unbranched alkanes. So notice that we have the molecular formula, so methane. We start with methane, that's its name. And CH4 is its condensed structural formula. Ethane, notice these meth, eth, pro, bute, pent, hex, hept, oct, non, and dec. We've seen these prefixes before. Those tell us how many carbons are in that straight chain. So methane, you would think, okay, what's a methane molecule? Meth means 1, so it's just going to be C bonded to 4 H's, and that's CH4. Ethane, you would think, okay, what is ethane? Ethane means 2, so I have 2 carbons connected to each other. And then you have to fill those in with hydrogens. And I could draw those out, but we could just count. That should be 1, 2, 3, 4, 5, 6. So overall, yep, we've got C2H6. And the condensed structural formula, you would write CH3, CH3. You can go down the group to check these. Let's look at butane here. Actually, I'm just going to, how do I add a page? Might I add a page to this? That's okay, I don't need to right now. If we look at butane, Same process should go through your mind. What does butane mean? But means four, and it's one, two, three, four connected together. Again, these are unbranched, straight chain style alkanes. They're connected in a straight line. So if there's four of those, there's got to be one, two, three, four, five, six, seven, eight, nine, 10 hydrogens, C4H10. They all have that same style. So if you go back to this page here, they have this formula. So the molecular formula for these straight chain alkanes, CnH2n plus 2. So if you have a, I don't know, pentane would be 5. So it'd be C5. 2 times 5 is 10. And then you had 2 more, so 12. That would be its molecular formula. And we go check our work here. Pentane, C5H12. So if you go up, hexane, C6H14, and so on. So those are our first 10 unbranched alkanes. And you can go longer than this, but you won't need to recognize any more than just these first 10. You should know, though, what is hexane. You should be able to tell by this versus this. Hexane is 1, 2, 3, 4, 5, 6. There's no branches, so we call that hexane. And notice they all use this ane. So these are, again, alkanes. We use meth and then we use A and E. We use prop and then A and E. So if it's an alkane, nothing but single bonds. So that's important. We've got nothing but single bonds. That's why we call it an alkane, ethane. And we use these Greek or Latin prefixes. This is important here, we're going to talk more about this. Any atom or group that would take the place of a hydrogen atom is a substituent. So we've seen molecules like this. We've seen ethanol. What is ethanol? Well, that's let's see, 2 carbons. Eth means 2. Anol means it's an alcohol. We have an OH group. So in this case, if I was just writing ethane, that would be ethane. But this is ethanol. So I'm replacing an H with an alcohol group. And this would be ethanol. So this is a substituent. And then sometimes you might have, instead of a hydrogen coming off of here, let's say you have, I don't know, a long chain here. You could have another carbon chain coming off here. Maybe this is a CH3 group over here. I'm not going to fill all these in, but assuming those are all hydrogens. We'll call that an alkyl group. Any kind of carbon and hydrogen containing group coming off of something would be an alkyl group specifically. So what are some common alkyl groups that come off of things? Well, very similar to methane, if we have something like CH3, we call that a methyl group. If it's an eth size group, 2 carbon chains long, that's an ethyl, and we go up, propyl, butyl, etc. Then we have some special ones. So notice propyl, for example. Propyl can be a straight chain, 3, or it can be 2 carbons and 1 carbon coming off of here. So that's called an isopropyl. Same thing with a butyl group. We could have a butyl group, or we could have an isobutyl group. This is called a sec butyl, and this is a tert butyl. So there's different ways to branch off these alkyl groups. We refer to them specifically as these type of things. And they all are determined, again, by how many carbons are in them and using these prefixes. So how in the world do we actually systematically name this stuff? Well, it really comes down to, again, these prefixes. And if there are substituents coming off of this, we tell you in the name where they're coming off, at which carbon that is actually happening. So here are the rules for naming branched alkanes. Remember, these straight chains are pretty easy to name. If I see this and there's nothing coming off, right, there's no substituents, it's all hydrogens, saturated alkane. You just count these up. 1, 2, 3, 4, 5, 6. 6 means hex. This is an alkane, so it's just hexane. Pretty simple. But what if, for example, I have, I don't know, let's say I have an OH group coming off of it right there. Well, that changes what this compound is called. So before, this was just simply 1, 2, 3, 4 butane. Well, now I have an alcohol. That changes it specifically to something different. The key with naming things is we want to be able to look at the name and draw the molecule from the name. That's the whole point of naming these things correctly. So the name, though, is based on the longest continuous chain. So you always count up how long the continuous carbon chain is. And that's the parent name. Like if it's 5 long, we have to use pent as our prefix. And then the branches are made up of hydrocarbon minus 1 atom, and we change those to ane to ol. So if we go back here, if we have a methane group, remember a methane would look like this, but if it's 1 carbon less coming off of a chain, right, this could be connected to something. Oh, oops, sorry, let me redo that. Let's say we have a carbon chain going this direction. This would be now a methyl group. That's what we would call this. 1 carbon branch, CH3 is a methyl group. But if you have 2, this would be our ethyl substituent. So let's actually look for these. This is going to make a lot more sense. We actually look at some. So let's name some of these. This first one is, and it shows you 2 incorrect ways to do this. So the position of a branched group on the main chain is identified with a number. And you could name it 1, 2, 3, 4, 5. You can count that direction, or you can count 1, 2, 3, 4, 5. This is the correct way. By convention, we have to be consistent. We put this number 2. We say this is at the 2 position, not at the 4 position. We use the lowest possible number to name this. So 4-methylpentane, technically that would work. But to be correct, we're going to count 1, 2, 3, 4, 5. So 5 long, that has to be a pentane. And then we tell you 2-methylpentane. So if I just saw just this, I should be able to draw this. I know that that's a pentane, so I would draw out a 5-carbon group. And then at the 2 position, you could draw it here or here. It doesn't really matter. You could draw it on this side or this side. It's the same molecule. But in this case, you could draw it like that. It would be 2-methylpentane. Let's look at a couple other ones here. This is 1, 2, 3, 4, 5, 6 long. Notice if I count this 1, 2, 3, 4, 5, 6, that would also be okay as well. It doesn't really matter which way you count it. Then this would be the substituent. But notice we're going to use this as our longest chain. 1, 2, 3, 4, 5, 6. 6 is going to be hex. So we call this a hexane. You can write that down first. And then what position is this substituent at? So we use the lowest possible numbering, not 1, 2, 3, 4, 5. You're going to use 1, 2. And we're going to write 2-methylhexane. Now, what if there are multiples of these groups? That's no big deal. Now we just tell you where everything is. So this is still a 1, 2, 3, 4, 5, 6 or 6, right? We're going to just name it this direction. And now we're going to tell you where everything is. Again, starting with 2. And now we actually have one at the 5 position. So we have 2, 5 dimethylhexane. That tells us there's 2 of these methyls, and they're at the 2 and 5 position. So all the information is tied up to draw this from here. Okay, so at this one, I would pause the video. Pause the video and use those rules to figure out what the names of these compounds are. So I'll give you a second to do that. And now that you're back, let's actually go through these. So name the following organic compounds. Well, first step, count longest chain, right? So for this one, let's see what we can do here. So 1, 2, 3, 4, 5. No, okay. 1, 2, 3, 4, 5, 6, 7. Is there any way I can get a longer chain? 1, 2, 3, 4, 5, 6, 7. Nope, that's the same length. So yeah, 7. So I'm going to use this as my chain. 1, 2, 3, 4, 5, 6, 7. So what in the world is a 7? Let's go back to that list. This should be hept. There it is. So this is a heptane group. So we've got 7 long. So we're going to use heptane as the parent name. So I'm going to write that out. Heptane. Okay. Now, what is attached to it? Do we have substituents? We do. We have a substituent here and here. So how do I tell you where they're at? Well, there's 2 ways I could do this. I could count 1, 2, 3, 4, and say there's a 4, and then 5 and a 6. But remember, we want to start name these at the least number possible. That means I want to number this like this: 2, 3, 4 position. So now I have a methyl group at the 2 position and a methyl group at the 4 position. And remember, I'm going to use the word di. So I will call this 2, 4 dimethyl heptane. Yeah, it's all kind of crammed together there, but that's what we call this. 2, 4, and I forgot the dash, dimethyl heptane. That gives me all the information to tell me I have a methyl group here and here. Now, what about the one down here? Well, first step, I need to count the longest chain. So 1, 2, 3, 4, 5, 6, or 5, 6, or 5, 6, doesn't matter which way I go. It's just nice to kind of keep it this direction. It's easier to look at it. Notice though, I could have named it 1, 2, 3, 4, 5, 6. I would get the same result. I have 2 methyl groups coming off this same position, but I'm going to name it straight because it's kind of easier to deal with. So it's 1, 2, 3, 4, 5, 6. So I'm dealing with a hex, some sort of hexane. Now I need to tell you where the substituents are. Again, I wouldn't number it 1, 2, 3, 4, 5. I would number it 1, 2. So at the 2 position, what do I have? I've got a methyl group and a methyl group. So they're both at the 2 position. So all I have to write here is 2, 2. It's showing you at the 2 position and the 2 position that I have a dimethyl. It might seem weird to do 2 and 2, but that's the convention. 2 and 2 telling me there's 2 separate one of these. Dimethyl hexane. So naming straight chain hydrocarbons isn't too bad. It's just that recognizing the longest chain is important. Getting the numbering correct, instead of numbering it 1, 2, 3, 4, 5, we remember to number it 1, 2. And then for these di groups, you need to make sure you list off every number and the di species. So that is naming alkanes. So far, these were rules, basically set 2 of 5 of kind of like pages of rules. So I'm actually going to pause the video here, and I will pick up in the next lecture for the next set of naming. And I'll see you guys then.